Hi guys. So in this lecture, we're going to be looking at dimensional homogeneity. Okay. So if you remember the conceptual introduction video, I listed dimensional homogeneity as one of the applications of dimensional analysis. So in this video, we're going to finally be able to look at it more in depth. Okay. The whole principle, the whole concept of dimensional analysis is on what we're going to be doing now, dimensional homogeneity. So we're going to look at what it means, the definition, and how we'll be able to use it to derive and validate certain equations that we have. Okay, so let's get straight to it. The first thing I'm going to ask is this equation correct? Okay, so this S stands for this displacement. Okay, pardon that. So U is initial velocity. T is regular time, and A is acceleration. Okay, so as an engineer, as a scientist, as a physicist, what are you going to do when presented with this and someone asks, is this equation correct? Are you going to set up your own, experimental get up, put on some sort of control experiment? Okay, let's say you've got something you can measure how fast it goes, say a little tram. You have a speedometer for velocity, have another one for acceleration, put it on a line track, frictionless track. You time it to make sure you're able to get the precise time, and so on and so forth. And once you're doing that and you end up with your graphs, okay, let's say you've got something that looks like this and this way, you're now going to be able to compare and interpolate and say, okay, I can show that this equation is wrong. But for those of us familiar with equations of motion, we know that the real thing is actually S is equal to UT first half AT squared. This is the correct equation. But when presented with something that looks like it can be correct, because these guys kind of look alike for someone that isn't particularly familiar with this, how do you verify an equation is correct? So that's the strength of the principle of homogeneity, which is what we're going to be looking at here. Okay, we take each term, we find the equivalent dimension of this term, and by all means, it has to add up. It has to be equivalent. It has to be the same as the dimension of the term it is being equated to. So that's what we're going to be looking at in this video. The homogeneity principle. Okay, so this is can get very hard to pronounce, but it's from homogeneous, to be the same thing, to be of the same nature. So the homogeneity principle says that a physical equation is dimensionally homogeneous if every term in the equation has the same dimensions. Okay, so let's say you've got some equation, okay, like I wrote in the last lecture. So let's say we've got y is equal to ab plus c plus root d plus k squared. Okay, this is some arbitrary equation. Okay, so for the homogeneity principle to be satisfied, every product term, okay, so usually instead of every term, is more appropriate to say product term, okay, since we're so many different products here. Every product term in the equation has the same dimensions. So let's say y has dimensions LT, okay, length times time. Then by all means, AB must also have dimensions LT. C must have dimensions LT. Root D must have dimensions LT. And K squared must also have dimensions LT for the homogeneity principle to be satisfied. If this is not held, let's say AB is LT squared and K is MT. Okay, what are we implying? It's like trying to say, what is the sum of, so let's say X is, okay, so let's say X is 3 kg plus 4 kg plus 9 seconds. So this is what you're trying to say equivalently when the homogeneity principle is not satisfied. You're adding things which cannot be added together. It literally makes no sense. So for things to be added together in such and such a manner, the dimensions of each of these must be equal and be equal to what it is being equated to. But in an equation where you have only one product term, which is why I included the term product here, after not putting it here, added product term. because not every term, because let's say we have AB here. Dimension of A may be L, dimension of B may be T squared, which now form LT. Okay. Dimensions of A may be L, dimensions of B may be T, which will form the equivalent LT that we're looking for to make these guys equal. Okay. Doesn't mean that since dimensions of A is L, that homogeneity principle is not satisfied. So friends, let's say we've got y is equal to ck over m. Okay, this is the only term in this equation. Then for the homogeneity principle to be satisfied, then ck over m must have the same dimensions as y. Okay, so it also applies for single term equations. It doesn't have to be a sum of products. An equation is homogeneous if every term in the equation has the same dimensions. So let's get to applications of this. The coolest thing, or the most apt thing we can use the homogeneity principle to do is to verify equations. So let's do this first. This is one of the equations of motion. So S is ut plus half at squared. So let's try and do that. We'll first of all find the dimensions of what is being equated to. So S is a length, which is displacement, which has dimensions L. Okay? So the first product term is ut. So ut is velocity times time. Okay? Velocity times time. So that is, because velocity is length per time. So that's LT minus 1 times t. If we were to write this out as a fraction, it would be L over t times t, which is going to be the same as L. So we know that the dimensions of ut has dimensions L. So this is the first product term. The second product term is going to be half at squared. And remember what we said about constants in the introductory lecture, that constants have no effect, dimensionally speaking, when dealing with equations. Okay, so we're going to just look at dimensions of at squared. So that's acceleration times time squared. All right, so acceleration is velocity per time, so that's length per time squared, LT raised to power minus t, times time squared. You know, we're dealing with t squared, so that's t squared. Writing this out as a fraction, we can say L t squared times t squared. Cancels out, and we end up with L. So the dimension of AT is L. So we can see that homogeneity is satisfied. Displacement has dimensions L. UT has dimensions L. And half AT squared has dimensions L, which is really cool. We've just verified the equation, which is a much simpler, is a better approach than having to set up your own verification kits. Okay, so let's look at this for a moment. V is equal to U plus AT squared. Okay, we find the dimensions of what is being equated to. Know that V is velocity, so that should be L per time. Our first product term is U, so U is also initial velocity, which is length per time, which is really cool. And then second product term, that's AT squared, is acceleration times time squared. And acceleration is length per t squared times t squared, which is going to give us L. So V for this equation has units L per time, U has units L per time, and AT squared has units L. So you can see that homogeneity is not satisfied. So there's no way, absolutely no way, that this equation can be correct. Cool. So for those of us that know equations of motion, you don't even have to know that to be able to guess what I can do to make this equation valid. So I'm trying to see that I'm equating this to L per time, and here I have t squared cancelling out L per time squared. If I were to take away one of these indexes and just leave it as AT, then I'll end up with L per t squared times t, which will just be LT minus 1, which will give me V is equal to U plus AT, which is actually the appropriate expression for final velocity. So though this is not an advisable method to use to verify the correct equations, because we know what this is meant to be, we can sort of look at the changes we can make to the wrong equation that we got to give us what we're looking for. Okay, so that's how to use the homogeneity principle to verify equations. We're getting to more practical things now. I'm going to use it to verify the Bernoulli equation. Okay, if you recall the Bernoulli equation, no, we're dealing with fluid mechanics in this course. We're going to just dealing with one instance of it. So usually it's to be, let's say, P1 over rho g V1 squared over 2g plus the first height is going to equal to, so the second instance, rho g final velocity squared over 2g plus z2. So this is all going to equal some constant k. So we're going to find out, are these terms dimensionally homogeneous? So if you don't know whatever it is that is on one hand of the equals to sign, as long as you can show that each term in each product term on the left, on one side of the equation, they are dimensionally homogeneous with each other, then you can show that the equation is going to be dimensionally homogeneous with whatever constant is going to be on the other side. Okay, so we start with the first term. So this is the product head. So for the first product term, that's the pressure head. Okay, so for the first product term, so that's the pressure head. We have pressure over rho g. So that's P over rho g. Okay, you know, pressure is force over area. So let's see if we can make this easier for ourselves. Pressure is force over area. Okay, remember force is mass times acceleration. So it's going to be ml t raised to minus 2. And area is going to be length squared. So I'm going to end up with ml to the power of negative ml to the power of negative 1 t to the power of negative 2. Okay, so we're able to show the formula, the dimensions of pressure. So pressure is going to be ml, let's take out the bracket since we're m l t raised to the power negative 2 divided by density times gravity. Okay, we know density is mass over volume. Okay, so it's mass over volume, which is going to be m for L cube. Okay, simple and straightforward. So that's m L cube times gravity. So acceleration due to gravity is an acceleration term, which is length for time squared. So that's going to be L t raised to the power negative 2. So it is very helpful to write out your terms this way. Okay, the formula for it, the physical expression, and then slowly, carefully end up with the final dimension instead of attempting to recall from memory, because that will lead you to problems down the line. So dimension of pressure is m raised from minus 1 t minus 2. Density is ml raised from negative 3. And acceleration due to gravity is lt raised to the power negative 2. Okay, so to simplify this, we will raise the terms in the denominator with a negative index and drop the terms in the numerator with a negative index. Okay, because if I have ml is for minus 1, it's the same thing as m per l. Okay, and if I have 1 over l t raised to the power negative 2, that's going to be the same as t squared over l. Okay, so let's see if we can do that. M cancels out, actually, first off, so that takes things off our shoulders. So we're raising L cube, so it loses the negative sign. So it's L cube, and we're also going to raise t squared. So L cube times t squared. Okay, this L stays down. Just remember that. Okay, we can even write it out first. And then look at our numerator, L. So this was L raised to the power negative 1. It's going to be L raised to the power 1 now. This was t raised to the power negative 2. It's going to be t squared now. Okay, so every term is covered. Simplifying this, t squared cancels t squared. This is going to end up being L squared. And these are both going to cancel out one term of this. So it's going to be L is about 3 minus 2, which is going to be L. Okay, which gives us L. So the dimension of the pressure head. Okay, so the dimensions of pressure over rho g gives us L. Okay, let's look at the next term. The velocity head. Okay, so velocity head. So that's v squared over 2g. So v squared divided by 2g. This should be much simpler. Because velocity is length per time. So we're going to try to square LT divided by, because we have no dimensions for constants. G is an acceleration. So that is length per time squared. Squaring this is going to give us L squared t to the negative 2 divided by L t to the negative 2. There's no need to simplify this. These are just going to naturally cancel out. And one L takes out one index. So the dimension of the velocity head, so that's v squared over 2g, is going to be L. Okay? Simple and short. And the third one is the positional or the elevation head. Okay? So that's the elevation. And this is just simply z. I know z is height above the ground. So the dimensions of z is going to be straight up L. So we have shown that the Bernoulli equation is dimensionally homogeneous, no matter how stressful that was. Okay? So pressure head has dimensions L, velocity head has dimensions L, elevation head has dimensions L. So whatever constant is on this side is going to have dimension of L. So that's all it takes. So now we've shown that the Bernoulli equation is trustworthy, at least with respect to the homogeneity principle. Okay, it's one of the checks you can use to verify an equation, and we've just shown that each product term in this equation is dimensionally homogeneous, shares the same dimension with each other. Okay, so we're going to look at a very important aspect, which is to show, do constants have dimensions? So this is the formula for the period of a simply harmonically oscillated body. Okay, so this is period, and we're going to try to see if constants have dimensions. So to make k the subject of formula in this, okay, so k is going to be t divided by the square root of L over g. Okay, so t is the period, L is the length, and g is the acceleration due to gravity. So and we know that k is going to be a constant. So let's show what is the dimension of this constant actually going to be. Okay, so we know t is period. Okay, and that's time over number of oscillations taken. So the period is going to have dimensions t. Okay, so that's going to be t. So let's get to work. Dimensions of k is going to be t divided by, and we're going to do a huge square root. Now we're handling L. We know L is length, so that's going to be L. And acceleration due to gravity. So G is acceleration. And we know we covered this. It's going to be L per time squared. Yep. L per time squared. So that's going to be L 2 raised power negative 2. Okay, to make this easier for ourselves, we can handle the negatively indexed denominator to raise it up. So it's a big square root. We're going to have L t squared over L. So this cancels out, and we're going to have t over square root of t squared, which is t over t, which is 1. So it's not necessarily that constants don't have dimensions. They just have a dimension of 1. And then including 1 in whatever calculation you're going to do isn't going to have an effect on whatever product it is. So that's just what I needed to be able to show, so that you're not sort of led to think that dimensions actually do have constants and they are being thrown away. So that's incorrect. When you're dealing with correct or homogeneous equations, okay, like this. So this has two product terms with one constant. As long as there's a constant here, the dimension of this constant should be unity, which is 1. So it's good that we've been able to show that. Okay, we're going to look at an important thing, which I hope has been coming to your mind since, which is one of the greatest limitations of dimensional homogeneity, which is what we just explained actually, the problem with the constants. Okay, remember our equation of motion for displacement s. So this is s is equal to ut plus half at squared. This is s is equal to ut plus 7 at squared. However, if we were to dimensionally check this, s will have dimensions L. Okay, ut will have dimensions L, since that is L per time times time. Okay, half at squared will have dimensions L, since this is L per t squared times t squared. Remember we said dimensions, constants don't have dimensions. If we're to check the second equation, s will have dimensions L, ut will also have dimensions L, and at squared would still have dimensions L, since 7 doesn't play a part. So the limitation of dimensional homogeneity is that it turns a blind eye to constants, physical constants in equations. So this might as well be s is equal to ut plus pi at squared or something like that, and this will pass the homogeneity test. So it is not a conclusive way of determining equation correctness, because this is a limitation. It turns a blind eye to crucial constants. We know that this is definitely wrong. But by turning a blind eye to this constant, we're able to show that some equations are wrong, but we can't determine with absolute certainty that the equations we're testing are, without a doubt, correct. Okay, so that's all. But before we go, solve a quick problem with a single product term. Okay, if you're willing to try this alone, you can pause the video and do this for yourself. But now I want to determine whether the equation for discharge is dimensionally homogeneous. Okay, so remember, this is volumetric discharge, which is Q, which is volume per unit time. Okay, so let's say this is volume per unit time. This should be L cubed T minus 1. This is the volume, this is the per time. So that should be for Q. A is the area. A is area. No, this is L squared. V is velocity. Yeah, okay. Almost thought that was volume. So V is velocity, which is length per unit time. So multiplying this together is going to give us L cubed per T. Okay, which is just something nice to do to show. So Q is equal to AV, although it looks kind of weird. What does volume flow have to do with velocity and area? It is still dimensionally correct. So we've been able to show and explain and take a deep dive into principle of equation and dimensional homogeneity to show that for an equation to be correct, it at least has to pass this test, which means that every product term has to have the same dimensions. Okay, we can't add 3 days plus 7 kilograms together to give one term. It doesn't make sense. So we've been able to show dimensional homogeneity, and the next video, taking off from here, we'll look at the Rayleigh's method of solving dimensional analysis questions. So thanks for watching, and I'll see you in the next video.